Okay, yes, thank you again for the invitation to give a second talk. Um, this talk will have very little to do with neutrinos. It's work I've been working on recently, and I think it's very useful for modelers who are interested in taking observational information about neutron stars and attempting to understand the underlying equation of state. So I'll begin with a few general comments. Um, for those of you who don't know much about neutron stars, most of them are pulsars, rapidly rotating and highly magnetized stars. What we really want to understand is what's going on at the centers of these stars. And there are several regions in the stars, and the outermost regions are where the X-rays come from which we get a lot of mass and radius information. The pulsars beam like lighthouses, and as a result, if they're in binary systems, we can get a lot of information about the characteristics of the binary and thereby determine the masses of the stars. So we believe that the radii of most neutron stars are near 12 kilometers, but there's probably a 25% uncertainty, 20 to 25% uncertainty in that number. And what we want is to obtain that number to much higher precision. We also would like to know what the maximum mass of neutron stars are. And with those two quantities, we can say a lot then about what the interior of the neutron star might be. So the minimum possible neutron star mass is only 1/10 of the solar mass, but none are observed to be less than about 1.1 solar masses, and we don't believe that it's possible to form a neutron star from a supernova with a mass less than about 1.1 solar masses. So the binary pulsar J0737 is an example, the only known example of a pulsar that's in a binary with another pulsar. And as a result, there are several general relativistic tests that can be used to determine the masses of the components. So this is taken from a few years ago, and these different lines basically represent constraints on the masses coming from different general relativistic tests. For example, the Nobel Prize was awarded for the observation of gravitational orbital decay, and that pinpointed the masses of the two components to be along this line. We can also see periastron advance in the system, which is much, much greater than that in the case of Mercury. Mercury is 43 seconds of arc per century. In this binary pulsar, it's something like 20 degrees a year. So it's by orders of magnitude much, much larger. We also observe, because the system is edge-on, Shapiro time delay, which is the extra time that it takes a pulse from the main pulsar, the more massive star, as it goes in and out of the line of sight of the other star. There's an extra or an additional or a smaller time delay. And so that gives us two quantities, one of which pretty precisely measures the mass of the companion star, and the other one is a combination of the two masses. There's also an additional kind of time delay called Einstein delay, which gives us another constraint that looks like this. And the fact that we observe two pulsars means that the mass ratio in the system is known quite accurately as well. So that's this straight line. So this little piece here is blown up by factors of hundreds. And we can see now that these lines are no longer lines, but they're bands caused by uncertainties in the timing measurement. And those bands will shrink with time as we observe the system longer and longer. So some of these constraints don't show up in here because when expanded, their bands are larger than this square. But the major ones that we see here are the Einstein delay, the gravitational orbital decay, and so on. And so where they all cross here is the final constraint on the masses. And you can see by the scale that leads to very, very precise measurements of the masses of the two stars in the system. So for astronomy, this is extremely interesting that one can get such a precise measurement of the two masses. And in fact, one can say that they are the most precisely known masses of any astronomical object, including the sun. Yes, that's right. And a precise test of general relativity that they can be determined so precisely. So overall, pulsar masses range from about 1.1 solar masses up to about 2.1 solar masses. These are the individual masses and the names of the individual pulsars. And the histogram here basically shows that most of the masses are concentrated in stars around 1.3 or 1.4 solar masses. Now, several other neutron star masses have been measured by other means, including the so-called black widow pulsars that appear to have masses up to 2.5 or even 2.8 solar masses. But the uncertainties in those systems are so large that they're not included yet in such a figure. And there is a recent determination of a mass that's supposed to be smaller than 1 solar mass, again with very large uncertainties. But there's a lot of debate in the community about the optical observations that go into the determination of the mass of that system. So we don't take it so I don't take it seriously, at least at the present time. Now, how do we measure radii of neutron stars? Well, one obvious way is to use X-ray observations of a quiescent neutron star, one that's not flaring or bursting, in a low mass X-ray system. And if you can measure the flux, which is the luminosity divided by the area of a sphere connecting us with the object, and if it's a black body, then that will be proportional to temperature to the 4th power times the radius squared. So get a quantity that's proportional to the radius divided by the distance to the star, the angular area, times temperature to the 4th. So then if we can measure the temperature, because the spectrum looks something like a black body, so we can estimate the temperature from the peak of the X-ray spectrum. And if we have a way of measuring the distance, then we can get a measurement of the radius. Now, general relativity introduces a mass dependence into this result. So what we can actually get is a measurement of radius and mass in combination. Another kind of X-ray observations can be made for systems that contain a neutron star that is occasionally bursting. And if the thermonuclear explosion on the neutron star surface is large enough, it actually exceeds the so-called Eddington limit, which is the flux necessary to raise basically the opacity is large enough that the surface layer will be raised above the surface of the star and then will fall back. And in Newtonian gravity, the Eddington flux is simply the mass divided by the distance squared. So again, and general relativity will introduce additional corrections to this that depend on the radius of the star, a redshift factor mostly. And so we see if we have two different measurements of these quantities that we can, for the same system, for example, we can infer the mass and the radius if we understand the distance and can measure the temperature as well. More recently, more precise measurements of neutron star radii have been obtained by using X-ray phase resolve spectroscopy. Basically, millisecond pulsars are observed to have non-uniformly heated surfaces so that when they rotate, hot and cold spots go in and out of view. And by observing these at different wavelengths, one can get both mass and radius information from them. And the three systems that have been studied so far in detail are pulsar J0030, for which the mass is not independently measured, and two pulsars for which the masses have been determined by pulsar timing. So J0437 is the closest and brightest millisecond pulsar, and J0740 is actually the most massive known pulsar with a small error in its measured mass from pulsar timing. So this is very important because these two stars are around 1.4 solar masses, and this star is in excess, a little bit in excess of 2 solar masses. So it's interesting then that we can measure the radii of two quite different mass stars, and I'll have more to say about that later. Now, gravitational wave observations of neutron star mergers can measure very precisely what's called the chirp mass. In the case of GW 170817, we observed over 10,000 orbits, and so the chirp mass is known to much better than a percent accuracy. And it's a sort of average of the two masses of the stars, and basically told us that the total mass of the stars in the system is about 2.7 solar masses. But there's also weak evidence that there are deformations of the stars as they inspiral. And from that, we can measure what's called the tidal deformability, or actually a combination of the deformability of the two stars, known as the binary deformability. And that has a very close association with the radii of stars that are, so from this chirp mass, and the total mass is 2.7 solar masses, we therefore suspect that each star has a mass in the neighborhood of 1.3 to 1.4 solar masses. And the radii of 1.4 solar masses can be connected very closely to the chirp mass and to the tidal deformability, this binary tidal deformability. And notice the approximate 1/6 power on this. So even a poor measurement of the tidal deformability can give very important information about the radius, because the errors are then reduced by a factor of 6. And finally, one can measure in binary systems like J0737, where we see spin-orbit coupling. If this can be measured precisely enough, general relativistic effects will be able to determine the moment of inertia of at least one of the stars in the system. And since the moment of inertia is roughly proportional to the mass times the radius squared, again, and the masses are in this system are known very precisely, we get therefore an inference of the radius. So there are three systems for which spin-orbit coupling is measured and for which the moment of inertia measurements are theoretically possible at present. J0737 has a binary period of 0.1 day. This system has a period of 0.16 days. And this newly discovered system has a period of only 0.08 days. So it has the potential of measuring this quantity to even higher precision than J0737. The first measurements of this indicate that the moment of inertia is more or less what we expect, but the uncertainties are quite large, about a factor of 2 at present. So it's not useful information for constraining the radius yet, but that day will come. So the summary of the best astrophysical observations of the radius so far are a combination of the gravitational wave measurement from GW 1708-17, which basically gives this sort of roundish contour. There are actually two stars in the system. The upper lobe here corresponds to the mass and radius of the more massive star, and the lobe down here corresponds to the mass and radius of the lower mass star. The mass ratio in the system is not precisely known. It could be anywhere between about 0.8 and 1, with a best value of about a mass ratio of about 0.95. And the three nicer systems that I talked about, which are using phasor-Zoll spectroscopy, the two solar mass star, there are actually 3 papers that appeared on the archive either today or yesterday that summarizes the latest observations of these stars. That's just a coincidence. I didn't plan it for this session. But these are 1 sigma. That's right. So the 2 sigma ones, of course, are larger. And what I find really fascinating about this is that you can think of a quantity, the difference in radii between 2 solar mass stars and 1.4 solar mass stars. If that quantity is positive, it indicates that the equation of state above the nuclear saturation density has to become very stiff. And if it's negative, which would be what you would think would be the usual case, as you go toward the maximum mass, the radius gets smaller, and that would indicate not so much stiffening at higher densities. But it's quite clear that these stars are all consistent with a radii in the neighborhood of 1.4 solar masses. That's almost a kilometer smaller than the 2 solar mass star. Yes. That's the usual case. If you have an equation of state that behaves something like pressure is proportional to the density squared, then in Newtonian physics, that would mean that the radius would not change as you increase the mass, but GR effects would cause the radius to shrink as you increase the mass. But if the pressure increases faster than the second power of the density, then it's possible that you can get a inversion of the mass radius curve, and the slope becomes positive. And then the two solar mass stars could have a larger radius. Well, yeah, so two solar mass stars is more likely to have strange material in it, but it wouldn't be a pure strange quark star. Undoubtedly, stars that are pure strange quark stars that have a lower, because the material has a lower energy at zero pressure than normal matter, those will always have very small radii. But okay, so we'll look at this again. But anyway, so this is a summary then of the three recent measurements of these three objects, in which the error bars have been reduced by about 50% from the measurements that were first made about 2 or 3 years ago. And this system, J0437, is a newly measured, for which the radius has been measured more precisely in the system, for which the mass is fairly well known from pulsar timing. So you can see these two stars have masses that are measured by pulsar timing with uncertainties of a 20th to a 10th of a solar mass. But this system, basically the most precisely determined quantity is the redshift, or the mass to radius ratio instead, which is what you might expect from measuring, getting X-ray information only about the flux from the star. So neutron star structure is a fairly simple task. The Tolman-Oppenheimer-Volkoff equations in general relativity that are the equivalent of the equations of hydrostatic equilibrium in Newtonian gravity are functions basically of only two aspects of the equation of state: the total energy density and the pressure, such that if you have an equation of state, which we would basically call how the pressure changes with energy density. So on the left graph, the energy density is in units of the density, energy density at the saturation density, which is in mass units about 2.7 times 10 to the 14th grams per cubic centimeter. And as an energy density, it's about 150 MeV per cubic Fermi. And here's the logarithm of the pressure in the same units, MeV per cubic Fermi. And the idea is that you have to begin these integrations at the center of the star, where the mass and radius are both zero, and the pressure and energy density have some central value, and you integrate down this curve until you get to zero pressure and zero energy density, and that produces a star with this mass and radius. And so on, if you start with a larger central pressure and energy density and integrate through the star down to zero pressure, you get a star with a larger mass. And typically you would expect that you would get, the stars would shrink all the way up till you reach the maximum mass. And because the maximum mass is known now to be in excess of 2 solar masses, it turns out that to reach 2 solar masses, the equation of state is stiff enough that in this region, the radius does not significantly vary with mass, only by a few tenths of a kilometer over several tenths of a solar mass. But precisely what this particular radius is, it could be 10, could be 12, depends on the pressures around the nuclear saturation density. Precaution I showed, yes? Sure. This. So if you and that's dynamically unstable. That's just what happens when you integrate these equations. There's a maximum pressure that can support the star, and if you try to go beyond that, then the mass that you can support actually decreases, and so that's dynamically unstable. Will immediately in microseconds collapse into a black hole. Now it's interesting, I hadn't realized this until I explored these equations further, but I used to think that it was this term that as the radius got to be a larger and larger fraction of the mass, as would happen as you get a more and more compact object, a more massive object, that it was this term that's causing the appearance of the maximum mass. But it actually turns out that if you remove all the general relativistic corrections and do the same integration for Newtonian objects, you will also find that they have a maximum mass as well. So the existence of a maximum mass is not a purely general relativistic effect. In any case, the fact that the maximum mass is close to 2 solar masses is due to general relativity, because in Newtonian gravity, you would expect it to be more like 10 or 15 solar masses. Prakash and I discovered that there's a close connection between the radii of neutron stars and the pressure near the nuclear saturation density. Now, you might think the nuclear saturation density is the density we find inside of ordinary nuclei. Surely we understand the pressure of matter inside of nuclei, and in fact we do. That pressure is close to 0, but because it's symmetric matter. And a nucleus is basically in equilibrium with a vacuum outside of it. So the pressure inside has to match the pressure outside, or the nucleus would expand or contract. So the pressure is practically 0 inside of a nucleus. But a neutron star is composed largely of neutrons. So it's 96 or so % neutrons near the nuclear saturation density. And so the difference of those energies, because of the difference in neutron to proton ratios, known as the symmetry energy, produces quite a lot of pressure, and that's what supports the star. No, they're not self-bound. They're bound by gravity. But, oh, yes, that's right. That's right. But that also changes the neutron to proton ratio. So for these different equations of state, for example, for a 1.4 solar mass star, the predictions are that the radii of such stars varies anywhere from 9 to almost 16 kilometers. Now, a lot of these equations of state are archaic and aren't used any longer, but the fact is that's what they predict. But if you take the combination of the radius times the pressure to the -1/4 power and look at, say, the nuclear saturation density, or 3/2 the saturation density, or twice the saturation density, you find that there are significant correlations now that exist between the radius and the pressure. So this was the first example of a direct correlation between the equation of state of matter and the actual physical conditions or structure of a neutron star. And so several others have been found since, but this was basically the first time that a direct connection could be made. So as I said, there are now several different correlations involving neutron stars. One of the most spectacular is known as the I-love relation. Actually, it also involves the quadrupole moment of a neutron star. So the relation is actually known as the I-love-Q relation, discovered by Yagi and Yunus. And it's a relation that exists between the dimensionless tidal deformability of a star, shown on this axis, and the reduced moment of inertia, which is basically made dimensionless by dividing by the proper combinations of constants and the cube of the mass. And so this graph shows the results of plotting about 1,000 different equations of state, which vary in radii for 1.4 solar mass stars from 9 to, say, 15 or so kilometers. Yet this particular combination between the tidal deformability and the moment of inertia is nearly unique. The uncertainty in here is about 0.5% at most. So this is a spectacular correlation that comes about. So the tidal deformability here is a combination of the love number, and then, which is the dimensionless number, and then there's a compaction factor here. So you can see that the tidal deformability is proportional to a very large power of the radius. You can also find a correlation if you look at F mode, the properties of F modes in neutron stars. So for example, the real part of the F mode frequency corresponds to the actual vibrational frequency. And here's the moment of inertia, reduced moment of inertia again. And again, you find a very strong correlation with uncertainties at the 1% or lower level. And the imaginary part of the F mode frequency is basically connected with the damping time. And again, they're accepted extremely low moment of inertias, which are basically for stars less than a solar mass and aren't really relevant. This part of the curve is the relevant part. And again, you see a very high degree of correlation. So these kind of correlations are really interesting because it allows you, when you're modeling neutron stars, if you have functions that are functions of both, say, the tidal deformability or the quadrupole moment and the moment of inertia, you can reduce the dimensionality of the system. And that's very helpful in modeling. Correlations also exist among nuclear properties, which are important for neutron stars. For example, the so-called L parameter, which is a measurement of the pressure of matter of pure neutrons at the saturation density, and the neutron skin thickness, which is the mean difference in radii between neutrons and protons in a neutron-rich nucleus. In this case, either lead-208 or calcium-48. And you can see that there are strong correlations between the quantities that make the neutrons stick out further in these nuclei and the pressure. And in a sense, this is an analogy to the fact that the pressure of matter also controls the radii of neutron stars. So the radii of neutron stars and the radii of nuclei, at least the neutron radii of nuclei, are both connected by the same quantity of the nuclear force. So it's interesting then to examine the structure of the mass radius curve per se. So we have a equation of state. Energy is a function of density, or pressure. Pressure is a function of energy density or mass density or energy density. At the maximum point, that's where the mass radius curve reaches a maximum. And if we take different equations of state, the dashed line or the dashed dot line, then we find different maximum masses and radii. It turns out that there's a strong correlation between the values of the energy density and pressure at the center of the star at the maximum mass point and the values of the maximum mass and the radius itself. And this has been revealed in a number of papers, including ones by Offenheim. What they did is they took samples of equations of state that are all quite different, producing all kinds of different mass radius curves, including a lot that don't even make two solar masses. Some of them don't even make one solar mass. Yeah, it's some kind of outlier in there, but it's the one that's down here. Yeah, I think that's the pure neutron, the ideal Fermi gas. That's right. So they find that you can write a simple relationship that connects the energy or pressure with the radius and mass with a couple of fitting parameters. And they achieve accuracies of about 3% in the energy density and the pressure just by knowing what the maximum mass and radius is. So this is interesting. If you know what the maximum mass and radius of a neutron star is, you can predict the pressure and energy density at the center to these sorts of accuracies. I'm going to skip the next part. They tried to do a better job more recently, and they suggested a little bit more complex fits of this form. And you can see the agreement works out to be pretty good, but the uncertainties are still around several percent. In fact, if you neglect this constant term, you can see that this is basically just a power law in mass. X here is basically the ratio of pressure to energy density. And this is basically then a power law in both pressure and energy density for both mass and radius. So we took several hundred equations of state, and refit this correlation. And so we find that the energy density can be written in this way. So you see the uncertainty is about, the 1 sigma uncertainty is about 5% in both mass, in both energy density and pressure from a measurement of the maximum mass and radius. And actually, and we also discovered that if you take fractional points along here, like at a fraction of 2.27 of the maximum mass or 0.76 of the maximum mass, that you can find similar correlations between the maximum mass and the radius at this fractional point with the central energy density and pressure of the center of this fractional mass star. Yes. But an M&R measurement is not equivalent to a measurement of central energy density and pressure. It can be a reasonable approximation, but you'll never get better than a few percent accuracy in this determination. As you can see here, mass radius curves can cross and pressure energy density curves can cross. And if there was a one-to-one connection between mass and radius and energy density and pressure, for example, this 0.2 would not show up as two different places in the pressure energy density graph for these two different equations of state. So you need some sort of additional parameter to improve this correlation. So we found actually if you take two different radii at fractional points along the mass radius curve, you can achieve accuracies in determination of the central pressures and energy densities of stars to much better than a percent accuracy in general. And these are analytic formulas. So the idea would be that you can actually analytically invert a mass radius curve. If you simply take fractional points along here, so first of all, you calculate a mass radius curve from an underlying equation of state. You take these fractional points, then you use these formula to calculate then the energy density and pressure of the centers of those fractional mass stars, and you connect them all, and you then essentially can invert the mass radius curve and get back to the original equation of state. So here's an example. Here's 4 different commonly used equations of state shown in different colors. So we computed then the mass radius curve from those equations of state. We used those analytical formulas to find the central energy densities and pressures of these different fractional mass stars, fractions of the maximum mass, and plotted them against the original equation of state. And you can see the errors are typically on the order of a percent or less in both energy density and pressure. So my student now has created this app where you can basically draw some arbitrary mass radius curve, and it will automatically then recalculate for you the underlying equation of state, which is you don't need to actually solve Tolman. And so this was tested with several hundred different equations of state. So that's a problem. I've always wanted to have this tool in class to just draw a mass radius curve and have the underlying equation of state show up. And if you make a little kink in the mass radius curve, what happens to the underlying equation of state? And that's a useful device. However, this doesn't get us immediately closer to what we do. And this same thing can happen for looking at the speed of sound at the center of stars of different fractional masses and the pressure to energy density ratio. Again, you can find fitting formulas that fit these quantities to on the order of a percent or better as well. But what we really want to do, we don't want to invert the mass radius curve itself, but we have observations, as I showed in one of the early slides, uncertainty regions in mass radius space. So how can we get back to information about the underlying equation of state from that? And we can't just go from the mass and radius and expect to find information about the energy density and pressure. We needed additional quantity, and that one candidate for such a quantity is actually what the slope or inverse slope of the mass radius curve is, namely dRdm. I chose dRdm because this dmdr has an infinity when the mass radius curve is vertical, while this has a 0 in it. And you can find fitting formulas basically of this form where a quantity like energy density, pressure, speed of sound, or whatever can be fit by knowing the mass and the radius and the slope at a single point, and with a much improved accuracy. So in particular, if you have two different mass radius measurements. For example, the 2 solar mass star measurement can be approximated as a double Gaussian with an uncertainty in mass of about 0.07 solar masses and radius of 1 solar mass. And the JO437 star, which is a 1.4 solar mass star with pretty good precision, has a radius of 11.7 with about a 0.8 or 0.8 kilometer uncertainty. If you take a random point in this mass radius space and a random point in this mass radius space, you can then calculate a slope common to both of these different points, and then use those previous formulas to calculate then the energy density and pressure for the centers of the 2 stars. So you get, this then is a realization then of the central energy and pressure with uncertainties predicted for this mass radius region, and this curve is a similar thing for this mass radius region. The traditional method is to use Bayesian inversion, where you basically generate a mass radius prior by generating millions of equations of state from a parameterization, and then sample all the parameters uniformly over some specified range. And then you see how well those individual equations of state in a Bayesian way fit those mass radius confidence regions. And then you then infer then what the most probable equation of state is. And so a typical calculation like that with these 2 different regions gives a pressure energy density band that looks like this. And so what we get with this analytic method is similar, but shows some differences and indicates perhaps that there is some model dependence that Rutherford et al. Have invoked in their choice of parameterization, because they're getting something that's a little bit stiffer than what we are, or maybe less stiff, because we would have a steeper slope connecting these regions. So it's interesting, this is early days yet, and maybe somebody will be more clever and figure out how to do a better job of using this technique to get underlying equation of state information. I just wanted to finish with the important point about the importance of this difference between the radii of 2 and 1.4 solar mass stars. So at present, with these 2 measurements, it seems to be positive. The mean value is 1.1, but there's 1.5 kilometer uncertainty in it, so it still could be negative. But here is a sample of 313 skirm and relativistic mean field forces that are constrained to produce stars with at least 2 solar masses at the maximum mass. And you can see here that this histogram shows what delta R is for each of those equations of state. And so basically this is 0, and so the number of these equations of state that predict the positive value of delta R is very small compared to the typical equation of state. So it's only the stiffer ones that can actually fit these average properties. Now the uncertainties here are still quite large, so we need better information to be more definitive. But early indications are now that I think the equation of state, 2 to 3, 4 times the saturation density is going to be such that the speed of sound is squared is a half or greater. It's going to be relatively stiff in that sense. So just to summarize then, this analytic inversion of the TOV equations has some nice features, and as a toy is interesting, but you can also use it to try to get particular information about the underlying energy densities and pressures associated with these different mass and radius regions. And it avoids the problems coming from the unquantified systematic uncertainties in this traditional method, which depends on the sampling of parameters and the choice of parameterizations that you use. I mean, there are all kinds of parameterizations. You can use piecewise polynotropes, constant speed of sound. There's the anyway, there's several different techniques in common use. And you can use correlations that also exist with the speed of sound to improve information about the underlying equation of state. You can also find correlations which we haven't explored too much yet, but the tidal deformability, the moment of inertia, binding energy, and so on also have correlations with mass and radius And so direct measurements of these can also be used to infer underlying equation of state information as well by the same general procedure. So although this talk has nothing to do with neutrinos, I thought it might be interesting to give a sort of general overview of what you can do still with a pencil and paper, basically, and not have to go to machine learning and so forth to, I think, to try to get useful information. So thank you.
Thank you very much, Jim. Questions or comments? Just a second.
Can you show me the plot where you for the sound speed that you mentioned?
This one?
Yeah. So if I am not wrong, that there is some bound on the CS square from the causality limit, which tells CS square should be less than equal to 1/3. And so there is some region where you are getting some greater than 1/3. So can you tell me something about that limit, or if it is very serious, so people.
Okay, so all these equations of state predict at higher densities that the speed of sound is greater than this limit of, square root of 1/3. And it's actually very difficult to produce two solar mass stars with the radii that we think are now indicated around 12 kilometers with an equation of state that does not reach that square root of 1/3 speed of sound barrier. It's extremely difficult to do that. So these typical equations of state show that quite clearly, that they get to rather large sound speeds by the time they reach the maximum mass. In fact, some of them exceed. The SCRM ones, there's one that exceeds causality at the center.
Can you show me the plot where you showed the variations of the tidal deformability?
This one?
Yeah. So you mentioned this error. I'm not understanding, what does this error mean? The error of lambda?
So lambda is basically the amount by which a star will deform in a tidal field. Okay, expressed as a dimensionless number in scale with mass. And the moment of inertia, I bar, is basically the moment of inertia also scaled with mass. So when you form these dimensionless quantities scaled with mass, it turns out they have a surprising one-to-one connection with each other. Although they involve different solution of different differential equations that you solve together with the TOV equation. In a sense, they're higher moments of the integral that produces the mass. They're a higher moment of the radius. But it doesn't seem to matter whether it's the third moment or a fifth moment. They end up with the same kind of generic connection with each other. The same thing is true with the frequencies, vibrational frequencies of cold neutron stars. They also show this universal behavior, which is completely unexpected. I kicked myself that I didn't discover this relation myself, because I like playing with these things. But Yagi and Eunice, when they found it, I looked at it and I said, no, that can't be true, but it is. And it holds for stars with large first order phase transitions as well. And for strange quark stars, it also holds. It holds for any equation of state. It's amazing. Any equation of state that's causal, I should say. Yeah, this is completely theoretical. Yeah, so it's true for a strange quark star, a bag model star. You just can't violate causality, and you can't. No, you can't violate causality. Well, maybe you can, and it would still work, but I haven't tried it with equations of state that violate causality. But
Well, can this data be used to restrict some new physics, long-range forces eventually, or everything can be just absorbed in uncertainties in a question of state?
Well, one example of how these relations can be used are in the nicer interpretation of the nicer observations, which are measuring fluctuations in flux and trying to interpret the light curve and trying to infer a radius. The underlying analysis depends a lot on making models of how light emerges from the neutron star. So light bending has to be done from every point on the star in every direction, and then collect the ones that reach the Earth. Also, the stars are spinning, so they're deformed. So there's a quadrupole moment in the star. So the difference from sphericity has to be accounted for as well. But it turns out you can remove some of these parameters because of these relations. The moment of inertia of the star and the quadrupole moment are directly connected. If you know one, you know the other to high precision. So you don't have to use quadrupole moment, for example, as a parameter in your study. And so when you reduce your parameters now from 15 to 14, doesn't sound like much, but it is an improvement. And so if you can reduce the number of parameters by a few, then that works. The tidal deformability is an interesting case because you can see directly from this relation that it's very sensitive to both the mass and the radius in an inverse way. It turns out that K2 also depends on roughly 1 power of R over M, so that the tidal deformability depends on the inverse sixth power of the compactness of the star. So the first analysis by LIGO of the determination of the tidal deformability from GW 170817 did not assume that the two neutron stars had the same equation of state. And then we followed on with an analysis that did make this assumption, so we could immediately make this approximation, which is good to very high accuracy. And that allowed our calculations to become much, much faster than what they were doing. And so we beat them to the second. When we got to the second paper, including the effects of the fact that both stars have must have the same equation of state, we were able to do that much faster than they could, because the calculations were much simpler because of that reduction in parameter space. So these relations are not only theoretically interesting to find, but they do have practical applications. So I hope that answered your question.
If you apply this correlation to this analysis for the radius,
well, for one thing, it reduced the upper limit of the inferred tidal deformability by about 25%. So that would reduce the radius by about 5% or so from their upper limit, which was estimated to be around 13 or 14 kilometers, is probably more like 12.5. And that comes about from including these correlations. Well, not less than 12, but so I showed that the figure, which is an analysis that we did that includes this these correlations. So you can see it gets cut off at 1 sigma. The upper limit's about 12.5. Yes, this analysis uses it. The LIGO correlation, the 1 sigma correlation, extends out to 13.5 or so. There's a big tail on this. And that comes from two features. One is that they didn't include the equation of state correlation in the first analysis. And secondly, when they were modeling with lambda, they treated lambda, they sampled lambdas in a uniform way. And we chose to use log lambda instead of lambda, because if you take a uniform distribution of log lambdas, that's like taking a uniform distribution of radii, because there's such a high power between lambda and the radius. So they estimated a much larger mean tidal deformability than we obtained, because there's a lot more parameter space if you have a uniform lambda at large lambdas than at small lambdas. And when you take a log lambda distribution, the weight moves to smaller values of lambda. So this is just an example of what priors do to your analysis. You have to be aware of what the priors are doing. So you have to decide, is it better to be modeling such that your inferences concerns uniform radius or uniform lambda? And a priori, you don't know which one you should be choosing. So all these Bayesian inferences do have this bugaboo that you have to be careful with what priors you assume. So that's why this distribution tends towards smaller radii. And we also have a cutoff at smaller radii that simply comes from assuming that the tidal deformability cannot be produced by an equation of state that becomes acausal. That would allow lambdas, that would allow radii to go down to 10 or 9 kilometers, which they also obtained. But if you look at what it means for the equations of state to produce those lambdas, they're acausal. And they did not impose this causality restriction in the choosing of their priors. Yes. And that's right. That's right. Causality imposes a lower limit to the tidal deformability of about 90, in the capital lambda for a 1.4 solar mass star. That's right.
Okay. Sergio, maybe last.
Related to what I was discussing before, for instance, you can have take a very old neutron stars in regions where you have a relatively large dark matter density that can get captured and be heated up. And actually, you can look for all neutron stars with a higher temperature than are expected. And the accretion of dark matter depends a little bit on the neutron star, but you cannot absorb all the uncertainties of the equation of state into the uncertainty in the accretion rate in order to get heating that you can actually test. I mean, you can, the very old neutron stars should have a very low temperature, that we have a range of temperatures depending on the equation of state. The accretion of dark matter will depend also on the equation of state, but you can heat up the neutron star due to the accretion, the scattering of dark matter over what you would expect, even including uncertainties. So you can actually do something. I mean, it's very complicated in any case because you need to have very strong effects, but in principle, you can do search for new physics with this.
Actually, there are some studies where you can actually accommodate the dark matter, you can constant the Lagrangian, and you vary the pressure and the density from the free particles, and you accommodate the dark matter parameters within these limits. And then you can say, yes, my dark matter can be, the neutron star can be composed of dark matter either as a core or a halo, and they can satisfy this kind of observation limits.
Mhm.
So, these studies are.
That's a good point.
Okay. Other comments or questions? Maybe the last one, because I want to. Yeah.
The nuclear potential. I mean,
Mhm.
the nuclear potential that you consider. At some point, I see you speak about relativistic mean field and Schirme. Schirme, two body, three body. You have two body,
Right.
two body term, attractive, three body repulsive, but nothing else. If you have hyperon in the neutron star, what do you?
We just took, there are compilations in the literature of hundreds of SCRM models and relativistic mean field models. And we recently wrote a paper in which we basically made large tables giving all of these quantities and with a general code that's available online to calculate the properties of any of these equations of state simply by inputting their parameters. And so there were about 700 different SCRM and RMF models, virtually almost everything that's in the literature up till about 10 years ago. And we've added a few more since, but it's a pretty painstaking job to try to keep up with new equations of state because they appear daily, it seems. But in any case, it's a pretty large representation of what's possible. And they have, some of them are clearly unrealistic. They produce negative neutron matter pressures at saturation density. Some of them have incompressibilities that are 5 times the observed value from dipole resonances and so forth. But, we thought we should be inclusive and include everything that's out there just to see what general features would emerge from all of this. So if we restricted those equations of state in some realistic way, I'm sure all of these constraints on inverting the mass radius, we can probably gain another factor of 10 in accuracy if we just restricted ourselves to, maybe 50 of the equations of state that are realistic as composed to the 500. Yeah, I restricted them to produce 2 solar masses, yes. There were still about 400, 300 or 400 that survived that test. But they still had radii ranging from 9 to... about half of those, something. There's amazingly large number of forces out there that can produce very large masses, yeah. They generally have extremely large radii, 16 or 17 kilometers for 1.4 solar mass stars. Then it's easy to make 2.5 solar mass stars if you already have a lot of pressure at around the saturation density. Yeah. Okay.
Okay, so I think we can go on discussing with Jim even during the evening, since he will be joining to the dinner and visit. If you have further questions, let us thank Jim again.